In our video for today, we're going to be looking at a specific example of where charge is conserved and essentially moving into our next topic, which is circuits. A circuit is defined as a closed loop of electrical current. And so here's an example of a circuit. We have a battery, wires, a light bulb, things that you'd be familiar with a circuit, but this circuit is actually not on right now. It's kind of hard to see, but there's no light in that light bulb. And that's because this is what's called an open circuit. To close the circuit, we just have to connect it, and now we have the light that's there. Okay. So this is an example of where charge is conserved. The amount of charge that's in the circuit, whatever you start with, is the same amount you're going to end with. We don't use up charge in a circuit. It gets reused over and over again as it travels through the circuit. Okay. So before we dive too deep into circuits, there's a few vocabulary terms that you need to know. And the first is the one that was used in the definition of a circuit, which is current. And current is the movement of charge through a conductor. We use the symbol I for current, and the unit is coulombs per second. Most oftenly, this is called amps or amperes, named after the French mathematician. Most people just call it amps, or the symbol A. So if you want to think about current this way, if you can imagine a wire and taking what's called a cross-section of, so we're just going to look at one piece of the wire, and we're going to see how much charge flows by that piece in a given time. That's our current. So the change in charge, or how much charge flows through over time, that is our current. This formula is on your reference sheet. The second vocab term is called voltage, and it is the potential difference between 2 points. We use the symbol delta V to emphasize it is a difference, and the unit we use is volts or just a V. Okay. So when you have a battery has a potential difference. If you have a D cell, AA, AAA, or a C cell battery, they have a potential difference of 1.5 volts. And it should be written somewhere on your battery. You are looking for a 1.5 volt potential difference. And one way to think about a battery and voltage in general is through a hill. So imagine you're a charge on a slide and you get to slide down as you move through your circuit. Well, how do you get back up to the top of the hill? You need a battery. So this battery indicates that there's a potential difference between the top of the hill and the bottom of the hill. And to get back around, you need something to essentially drive you back to the starting point of the circuit so you can go through again. Remember, if you're charged, you're conserved. So the same charge is going to be used over and over and over again. It just needs something to drive it through the system. And that's going to be your potential difference. Okay. Last but not least is resistance. So if voltage drives a circuit, then resistance is what impedes it. We use the symbol R for resistance, and the unit is this weird sign. It's actually a Greek letter omega, and we call it an ohm, named after another mathematician, physician. Ohm actually is super special because he has his own law named after him, and this is Ohm's law. It's the relationship between these three primary vocab terms. Current is equal to the potential difference, or your voltage, over your resistance. Okay. You'll often find this relationship in graph form, where you have current and voltage graphed as so that current is equal to the voltage. Current on your independent axis, your voltage on your dependent axis. And when you graph it like this, you get delta V, equals I times R, where R is your slope. So if a graph follows this, we get the slope being the resistance. And this is what we call an ohmic resistor. So this is going to be this kind of resistor where you do have this linear relationship between current and voltage. Okay. However, if you have a nonlinear graph, it's still relevant. It's just called a non-ohmic resistor. And there's certain factors that affect this, one of which is temperature. You don't have to understand exactly why temperature affects it, but the longer you leave a light bulb on, the more voltage that you need in order to drive this current. Okay, so thank you for watching. In class tomorrow, we will be looking at the different factors that affect resistance.